What is up, everybody? Welcome to the Chapter 5 review. Um, if you guys are wondering why there wasn't a Chapter 4B review, it was because I just I just don't know what happened to the software that I was having these reviews on. It just deleted the review that I had, and so with like 2 days later, I couldn't just make an extra review. I don't have that kind of time, so. Well, now we have this chapter 5 review, and the chapter 5 review is spread into two distinct parts. One part is the proving and the disproving of identities while also solving the equations, and then the other part is the sine rule and the cosine rule, or the law of sines and law of cosines. So that's how I'm going to present it as. I'm not going to present it as little sections because that's not what this chapter is. Oh god. I'm going to present it as two sections because the chapter is pretty much just two sections. So, let's go. Here are all the identities that you should know, and you can get all of the identities from these identities. Um, for example, if you want if you want the identity, the cofunction for tan, it'll just be tan 90 minus theta equal cotangent because that's the cofunction identity for tan. So it works the other way around because they're co-functions, and I've already shown you with the triangle. I think, but basically, the co-functions means that if you ever have the angle in a triangle, if you take in a right triangle, if you take the sine, if you take the function of one angle, and then if you take the co-function of the other angle, you should get the same thing, right? So sine of angle 1 equal cosine of angle 2, right? Um, and that's why these cofunctions exist, pi over 2 or 90 minus theta, right? And then the Pythagorean identities, those can also be derivable. I actually derived them right there for you. It will be 1 plus cotangent squared theta equals cosecant squared theta, or tangent squared theta plus 1 equals secant squared theta, as well as the regular original sine squared theta plus cosine squared theta, right? And then there's the obvious identity. There's the obvious identities. I don't even know why I said obvious identities. Okay, there you go. There you go. There's all the rest of the identities. If you want to stop there. Um, there's the obvious identities, and then there's the odd even identities, um, where you have sine is an odd function and cosine is an even function. So just by knowing that sine is an odd function, cosine is an even function, you can already derive everything. But however, I did it for you because I'm nice. So these identities, right? If you put minus theta into any of these, you should be able to get these odd and even identities, knowing that sine of minus theta is minus sine theta and cosine minus theta is cosine theta. So these sum and difference identities, they're they take a little bit more effort to prove. I'm not going to prove them in this video, but these are the identities. So the sine alpha plus beta plus or minus beta, sine is the same sign, right? You can remember it because sine is the sign, right? Sine is the same sign, but cosine isn't because cosine is the cofunction of that, so it has to be the other sign, right? If you know what I mean. So sine is the same sign. Tangent is sine over cosine, so it's the same sign on the sine part, but it's a different sign on the cosine part. So it'll be tangent A, same sign, tangent B over 1 different sign, tangent A, tangent B, because it's sine over cosine. Sine is the same sign, cosine isn't, right? It's pretty ironic because in these half angle identities, It's not the same sign, right? Sine 1/2 theta equal 1 minus cosine theta, right? So sine in this thing, sine isn't cosine, so it has the minus in there, but cosine is cosine, so it has the plus in there, right? It's sometimes your the stuff that you remember don't really work. And then tangent is sine over cosine. You could just verify it in there to get these half angle identities. So that's it. We've spent enough time staring at this page, and I don't want to stare at it any further because I'm wasting time. So prove these basic identities. Let's start. Let's start using these. First of all, sine theta sec theta equal tan theta. What's sine theta? Sine theta is just sine theta. And then sec theta is 1 over cosine theta. So some of the strategies that I have, no, not sec theta. Some of the strategies I have whenever you solve some of these equations is you should turn them into sines and cosines. Right? Turn as many things as you can into sines and cosines. If you can't find any other way to do it, just turn it into sine and cosine. Right? Because there's no square, there's nothing here that's square. So you can't really do anything in terms of squaring or half angle, double angle. You can't really do any of that. So you can just turn everything into sines and cosines, then you'll be able to turn it back into the tangent or whatever you're trying to look for. Next, cotangent pi over 2 minus theta. That's a tan theta right there because of the other identity, right? So tan theta plus sine squared theta plus cosine squared theta, Pythagorean identity. So tan theta plus 1 is tan squared theta plus 1, which is equal to sec squared theta. That's it. Right, this was on the quiz, but there was no like trickery like this. This was just on the quiz. Sine squared theta plus cosine squared theta plus tan squared theta. So you should know how to do that already. Sine of minus theta, odd function. That will be minus sine of theta. Sine of theta. I should use a different pen, just in general pen color. And then plus cosine theta, and then cosine of minus theta is cosine theta because it's an even function. So that's minus sine squared theta plus cosine squared theta, which is cosine squared theta minus sine squared theta. And finally, we have sine squared theta, not sine squared theta. Oh god. Okay, anyways, we're back. We have our sine theta, cosine theta, tan theta equal 1 over sec theta, CSC theta, cotangent theta. Now, if you prove the identity, you can actually use any way you want to prove the identity. You can go from the left or the right. So I'm going to go from the right here. This is also equal to, well, 1 over sec theta times 1 over CSC theta times 1 over cotangent theta, right, times 1 over CSC times 1 over cotangent. And we know these identities are just 1 over 1 over 1 over 1 over cosine theta plus 1 over sine theta times 1 over tangent theta. Oh god. 1 over tangent theta. So what we can do is we can reverse these. Right, this is 1 times cosine over 1, so that will be just cosine theta multiplied by sine theta. I hope it's still in the frame. Yes, it is. And then multiplied by tan theta. And that is our proof right there. Sine, cosine, tangent. Pretty sure I don't need to move on anymore for you guys to prove that that's equal to that. And okay, we're fine. So level 1 questions. These are the easy questions. Now we're gonna try to solve these easy questions, and let's go. So we've got to simplify this fraction. We have 4 sine squared theta, right, minus, because we've got to multiply by sine squared over sine squared. I'm really lazy. I don't even want to I don't even want to write down the whole thing. the whole cosine or sine, right? Minus 2 cosine squared theta over, this is sine squared theta, cosine squared theta. And if you split the fraction, because you still want two things, right? So if you split the fraction, you'll get 4 sine squared theta over sine squared cosine squared, and then minus 2 cosine squared theta over sine squared cosine squared. So then you can cross those off, you'll have 4 over cos minus 2 over sine, or 4 over cos squared minus 2 over sine squared, which is equal to 4 sec squared theta minus 2 cosecant squared theta. And that is your first one. Second one, cosine of theta minus 30 equals this. This looks awfully similar to one of the sum identities, right? One of the identities. So we're going to do that. We're going to try to do that. I'm pretty sure, I don't even know if I actually did this right. If this is not actually an identity or not. It might actually not be an identity. Let me see. So cosine of theta minus 30, so cosine of theta, cosine of 30, plus, because it's different sign, sine of theta, sine of 30. And then cosine of 30, square root of 3 over 2. I'm not stupid, because I did actually get it wrong on the quiz. And then this is 1/2 sine theta. And this is different sign, so I don't even know what I'm talking about when it comes to the minus right here. So if this is supposed to be a plus, I'm sorry. So then if you combine them together, you'll have sine theta over 2, and that's the correct answer. I'm sorry, there's going to need to be a lot of cuts because people are miscommunicating. Okay, I am back. I'm sorry. I'm really sorry about the pauses. That happened. Okay, this is a plus. So this actually works, right? If I put a minus in there, it would have been impossible. Because I didn't see, basically. It's just I didn't notice that this was what it was supposed to be. I think I thought it was sine or something. I'm not sure. But let's continue proving. We have cosine theta equal square root of 1 minus sine squared theta. 1 minus sine, I'm going to use this part now. So cosine theta equal 1 minus sine squared theta is cosine squared theta, right? Because sine squared plus cosine squared equal 1. So cosine squared equal 1 minus sine squared. So then this is equal to square root of cosine theta squared, and then the square root cancels cosine theta. Right, cosine theta equal cosine theta. I should no, actually, yeah, I should say that it's this is the identity, not actually just cosine theta, because identities actually have all numbers of the domain have to have to work the same way. All numbers of the domain have to work the same way, right? So let's do this. Solve for theta. Sine squared theta minus sine theta minus 2 equals square root of 3 over 2. So we can actually factor this. We could do a substitution, but this is pretty easy to factor just in general. Plus 1 equals square root of 3 over 2. And I actually didn't do really well for this because I really shouldn't have put square root of 3 over 2 here. I should have put 0. Let's put 0. Because if I put square root of 3 over 2 there, it'll be pretty much impossible to factor. So 0. Sine theta minus 2 equal 0. Sine theta equal 2. Theta equal, there's no theta. Right, theta equals, well no, sine theta equal 2, and no solution. No solution. right? Whereas if you have sine theta equal cosine theta plus 1 equals 0, you have sine theta equal minus 1, which then will have theta is equal to the lowest angle that you can get, 3 pi over 2, and this is assuming it's in between 0 to 2 pi. If it's not, you can put 2 pi k right here. So that's it, right? For the first set of questions. For the second set of questions, let's go. Level 2 questions. They're a little, I guess they're a little harder. They're not much harder. Level 3 questions are the harder ones, I guess you could say. But level 2 questions aren't much harder. So we have sine x, cosine x, tan squared x equal tan x minus sine x cosine x. So what I advise to do first is, if you see a bunch of trigonometric functions like this, just convert into sines and cosines. So let's do that. Right, like this. Right, and then this is equal to sine to the third power x over cosine x. Right, and then this is equal to this is actually equal to tan x cosine tan x sine squared x. And since it's tan x sine squared x, we can actually convert this into tan x, and then 1 minus cosine squared x. Cosine squared x like this. And then this becomes tan x minus cosine squared x tan x. And then we can convert this tan x into the sine x cosine x. Right, this tan x equals sine x cosine x, right? So then we can cross that, and then we get tan x minus cosine x and sine x. I really thought I made a mistake somewhere in the proof, but I did not. And that's equal to tan x minus cosine x sine x. Right, so whatever you have that's already working with the thing, chances are it's probably going to continue working. Right, so cosine minus z over secant minus z plus tangent minus z. So then we'll have well, they're all minus z's, so we're gonna actually try to simplify them into their regulars, right, by using the identities. So cosine will stay z, secant will be z because it's the cosine, and then tangent has sines and cosines, so it'll be negative. So tangent minus tangent z. Now the secant I'll change into 1 over cosine, and the tangent I'll change into sine over cosine. Right, so this will get me, no it won't, it'll get me cosine z over 1 minus sine z, and then over cosine z again. Put the cosine on top, cosine squared z over 1 minus sine z, right? And then notice how there's only sines here, there's no cosine. So we'll do the 1 minus sine squared z over 1 minus sine z. And then this is equal to, well, difference of squares, 1 minus sine z, 1 plus sine z over 1 minus sine z. And then these cross over, 1 plus sine z. That's the correct answer. You know what? Should I do this? I don't want to do this. I really don't. Okay, I'm gonna do it though. I'm gonna do it. Simplify. I'm actually going to no, I'm going to get all of these. I'm going to make them smaller. Right? Accept this because I need this. Simplify sine x plus cosine x, sine x plus cosine x. And they're all to the 4th power. This is a little bit hard. This is actually a little bit hard. Now, if you know Pascal's triangle, that's what I'm going to use. You'll know what the coefficients are going to be of the whenever you finish expanding them. It is really nice Actually, this is x to the 0, x to the 1, x squared, x to the third, and then x to the fourth. You'll have 1, 4, 6, 4, 1, and then 1, 4, 6, 4, 1, right? That's what's going to happen. But we got to know which ones to cancel out, because there's going to be some canceling right here, because we have a minus right here, right? So basically what's going to happen is this is going to give me sine 4 to the x plus sine 4 to the x plus 4 sine 3x cosine x plus 6 sine squared x cosine squared x plus 4 cosine sine x cosine to the third power x, probably won't appear on the test, plus cosine to the fourth x. Now we're going to get the exact same thing right here. We're going to get the exact same thing, but the odd powers will have the negative, because it's taking one of these and then 3 of these, and then 2 of these, that's positive, 3 of these, 1 of these. There's one negative in it, so it's going to be negative. So therefore, we'll get sine to the fourth x minus 4 sine to the third x cosine x, right? So these are done, and then we'll get plus whatever, and then we'll get minus again, so these are done, and then we'll get plus whatever, so it'll be the same thing. So then our final verdict is it's going to be 2 times sine to the fourth x plus 6 sine squared x cosine squared x, right? And then minus and then plus again sine cosine to the fourth x. And can we simplify this any more? I'm pretty sure if you dig deep enough, you could simplify it any more, but I really don't want to simplify it. This is more just like a filler problem, honestly. But if you wanna simplify it more, you can simplify it more. I'm not gonna stop you from simplifying it more, because it's pretty cool. Pretty cool stuff. So we'll have right now. I guess you could turn sine fourth into all cosines. You could turn everything into the cosines, and then you could try to have like some fun, like cosine to the fourth. And then there's a cosine to the 8th power, and then you could like quadratic it somehow. Yeah, but I'm not gonna do any of that. No way, not gonna do any of that. So 2 sine inverse of x equals square root of 2. So how do you solve it? This is not even a level 2 question. I don't know why I put this into a level 2. X equals sine square root of 2 over 2, sine of the square root of 2 over 2. Sine of square root of 2 over 2 is actually not something that's actually in the domain of sine. Well, no, it is in the domain of sine, but it's not a nice number. So what I meant to say was 2 sine x. So we have sine inverse of square root of 2 over 2. The square root of 2 over 2, if you look in the unit circle, that's pi over 4 and 3 pi over 4. So all our answers are pi over 4 plus 2 pi n and 3 pi over 4 plus 2 pi n. But do not write this if the domain specifically only asks for 2 pi, 0 to 2 pi, or else you will not get it right. Level 3 questions. These questions are tedious. They're not necessarily hard, they're just tedious, right? Let's be honest. I'm going to be really honest. These questions are probably not hard, they're just going to be tedious. So, let's go. We have cosine of this minus this, and then sine of these. So cosine of pi over 2 minus x, cosine of y, right? And then add, or different sign. So add sine of pi over 2 minus x, and then sine of y. Right, this looks really, really messy, and honestly, I haven't solved this yet, so I might actually not even be able to do this, but we're going to expand it again. Right, this is going to be now cosine of pi over 2, which, before we even start, cosine of pi over 2 is 1. Right, so cosine of pi over 2, before we even start expanding this is 1, and the sine pi over 2 is 0. So we have cosine of pi over 2, cosine of minus x, so that'll be cosine of x, right? And then sine of pi over 2, which is 0, so that doesn't even count. So you'll end up having cosine x, cosine y, plus sine of pi over 2 minus x, which is, well, sine of pi over 2, cosine of minus x, nothing, and then cosine of pi over 2, which is 1, sine of minus x, which is minus cosine, minus cosine of x. So you'll have minus, or wait, sine of pi over 2. Yeah, this is not a good way to prove, you could tell, right? If you're proving, write everything down. Don't do it in your head. Sine of pi over 2 is 0. Sine of minus, cosine of minus x is nothing. Cosine of pi over 2 is 1. And sine of minus x is minus sine of x. So minus sine of x. Or plus sine of x. And then sine of 1. And somehow I proved it to be equal to cosine of x minus y. Is there a fundamental flaw in the question that I'm trying to do right now? See, sometimes these happen. I don't even know where I got the question from. So now I'm going to have to try to figure out what I got wrong. Because the correct answer is sine x plus y is equal to sine x cosine y over cosine x sine y. Pi over 2 minus x. That's cosine pi over 2 cosine minus x, sine pi over 2. Wait, let me see my identities. Yeah, different sign. Sine pi over 2 minus x. Okay, so, yeah, I don't really know what happened. Sine x plus y will give you sine x cosine y plus cosine x sine y. And then this will give you cosine x cosine y plus sine x sine y. So, the identity might just be a false identity. I might be struggling to be able to find the correctness in this identity. I took it somewhere from the book. I don't know where. I don't know if it's correct or not, but we'll move on. We'll pretend to set cosine. If you can correct me on this, please do. We'll pretend to set cosine. If you can find a problem on the book, please do as well. Because I am struggling. So cosine of 7.5 degree. What's cosine of 7.5 degree? It's cosine of 30 degrees divided by 4, which is also cosine of 15 degrees divided by 2, or cosine 30 over 4 degrees. This is not correct. It's not cosine of 30 divided by 4. It's cosine of 30 over 4 degrees, like this. So we'll find cosine of 30. What's cosine of 30? Square root of 3 over 2. Should be able to instantly find that out, right? But cosine of 30, we have cosine of 30, and then we have to apply it onto our formula, our half angle formula actually. So same sign, that'll give us 1 plus cosine, 1 plus square root of 3 over 2 over 2 over 2 over 2, which is equal to 2 plus square root of 3 over 4, which is equal to 1/2 square root of 2 plus square root of 3. And that's our first result from this mess. It's gonna get more messier. And then we take this, that's our cosine 15, right? We could actually make this a little bit less messy by doing 45 minus 30, but we're not doing that. So we'll take this square root inside of a square root, and actually I kind of want to do 45 minus, because it's a lot less messy. You'll get square root of 6 plus square root of something. Yeah, but we'll just use this. So we'll have square root now of 1 plus 1/2 square root of 2 plus square root of 3 over 2, which will give you, this is 2, so it'll be 2 plus square root of 2 plus square root of 3 over 2 over 2. Keep taking the square root of that. You'll have 2 move down to the bottom. You have 1/2 square root of 2 plus square root of 2 plus square root of 3. And that is your answer. 1/2 plus the square, 1/2 times the square root of 2 plus square root of 2 plus square root of 3. All nested into each other. Yeah, pretty cool. I could definitely simplify that if I wanted to, but I don't want to simplify that. That sounds like that's a pain to simplify. So we're not going to simplify that. We're going to leave it as is. Okay, we have our final identity now. So let's prove it. 2 tan x over 1 minus tan squared x. What's 2 tan x? 1 minus tan squared x. We have, this is actually equal to, this is actually equal to one of the identities, and the identity is tan 2x, right? This is tan 2x. I didn't actually put tan, I don't think I put tan 2x in there as an identity, because I assumed you could do it from tan x plus x. That's tan 2x. But that's not important, because we actually don't want to get tan 2x. We want, this is a bunch of cosines and sines. So guess what we're gonna do? We're gonna make it into sines and cosines. So there you go. And then add that to 1 over, well, just a regular, right? So I'll manipulate this fraction first before I try to add it to the other fraction. So this will get you, the bottom will get you, well, that's cosine, so it's cosine squared x minus sine squared x. And then I can multiply the top by cosine squared and the bottom by cosine. So this will be removed, this will be removed, and then you'll get a cosine x multiplier on the top, which will get you 2 sine x cosine x. The things I'm saying might actually be really confusing to you, but it works, because now this turns into 2 sine. This is actually sine 2x, and this is cosine 2x. And then plus this by 1 over 2 cosine squared x minus 1. But 2 cosine squared x minus 1 is cosine squared x, right? And then plus cosine squared x minus 1. Right? Am I not stupid? I might be stupid. Yeah, I'm not stupid. Okay. Which is, this is cosine squared x minus 1. And you know the sine, if you want the sine squared x version, right, the sine squared x version, you have to reverse the sign. 1 minus cosine squared x, like this. Now we have cosine squared x and the 1 minus cosine squared x, which will give you sine squared x. So now this is cosine squared x minus sine squared x as well. So then now what you'll get is 2 sine x cosine x plus 1 is equal to well, no, not is equal to cosine squared x minus sine squared x, like this, right? Now this is going to now we need this as the denominator. So what is the logical step? We will do the difference of squares at the bottom. Cosine x minus I'm sorry. I'm just gonna write c minus s now. C minus s, c plus s, right? And then 2sc plus 1. We want our cosine x plus sine x on top. So what we actually want to do is prove that this is cosine, this is a c plus s squared. And in order to do that, we can actually turn this 1. Right? We want to prove this is equal to c plus s squared, cosine plus sine squared. So we can turn this into sine squared x plus cosine squared x, which will get you c squared plus 2cs plus s squared, right? That's equal to cosine squared x plus sine squared x. So that's actually going to be cosine plus sine squared, right? Like a squared plus 2ib plus b squared. And then this is c minus s, and this is c plus s. So we can all together condense it down, c plus s over c minus s, and that is our identity. And that was extremely satisfying to prove, to say the least. That was really I do not actually prove these identities before recording, so I actually have to prove it and perform on the spot. And if you get these, if you get these during the recording, especially, it's really impressive, right? Not impressive. I mean, satisfying. It's not like these. It's like these. So let's go. Let's continue. Now we have extra hard questions. When I say extra hard questions, I really just kind of just taking a piss out of out of you and out of everyone else, because they're not really extra hard. They're just like special questions, right? We have cosh and sinh. You guys don't know what cosh and sinh is. It's the hyperbolic functions. So basically, instead of a circle, it's a hyperbola that all the functions will depend on, right? Instead of the circle that the functions depend on, x squared plus y squared equals 1. That kind of Pythagorean identity. You have x squared minus y squared equal 1 type of identity. So anyways, quit talking and we will do this. So if you remember your log identities, you have sec theta plus tan theta, and we can actually multiply this by sec theta minus tan theta, because that's a log identity right there, and that's equal to 0. And then that will get you sec squared theta minus tan squared theta, and we want that to be equal to 1 somehow, because if you take e to the both sides, you'll have 1. So sec squared theta minus tan squared theta. This is sec squared theta minus tan squared. That's 1 minus cosine squared theta, and then that's minus sine squared minus cosine squared. And then this is easy enough to prove. 1 minus sine squared, and this is equal to cosine squared. So cosine squared over cosine squared is equal to 1. So ln of 1 is equal to 0. And that's correct. Finally, we have e to the x. Actually, I don't even want to do these because they're really not in the question, but I'm sure. So we have e to the x plus e to the minus x, e to the x. Okay, so we have e to the x plus e to the minus x over 2 plus e to the x plus e. Okay, so basically I already wrote the 2 here. This is what the functions equal to, by the way. So cosine hyperbolic is equal to this, and sine hyperbolic is equal to this, right? And it follows the same rule, right? Cosine, it's the opposite kind of. So cosine has a sign, but sine doesn't have the sign, right? It's a little weird. So we have e to the x minus e to the x. That's just goes to 0. E to the minus x minus e to the minus x, that's e to the minus 2x over 2 is equal to 1. That's what we're going to have to prove right here. E to the minus 2x over 2 is equal to 1, and I honestly don't know how to prove it. Cosine cos squared x minus 2. Okay, I'm actually going to try to find a way to prove that this is a correct statement. Yeah, I probably have to find it using another way other than just this. If you guys can see, this is why I shouldn't do anything live ever. Because I got it wrong, right? And you don't combine it like that. So e to the minus x minus e to the minus x is 2e to the minus x over 2 equal 1. There you go. So now we can actually cancel this, and now we have e to the minus x equal 1, which still doesn't explain why everything's equal to 1. But at least it's a little better than so if we have e to the minus x equal to 1, then e has to also equal e to the x also has to equal to 1, x equal to ln1, which is 0. I don't know how you will use that, why you'll ever use that, but x equal to 0, and if you have 0 in there, the equation is correct, and if you have any other number in there, the equation is also supposed to be correct. Yeah, I probably proven this before in calculus, but I'm just too lazy to prove it right now, and I just proved it wrong. Oh, I know where I went wrong. I didn't square them. Well, that's going to be it for today's. No. Okay, I didn't square them. I'm probably gonna go back later and do it, or I'm just not gonna do it. So now we have equations, right? These are easier equations. We have sine 2x equal cosine x. Let's just do it. This is 2 sine x cosine x. And make sure you set them equal to 0, right? Big mistake is not to set them equal to 0 and then go look at the graph and see when they cross, and that doesn't work. It's solving algebraically, not graphically. So if you solve algebraically, you will have it work your way, and if you don't, you won't. So this will get you cosine x is equal to 0, which is easy enough. That's just x equal to the pi over 2 and the 3 pi over 2. Solve between 0 and 2 pi, so this time they don't want the 2 pi n. So this is 2 sine x minus 1 equals 0, which means sine x equal to 1/2, which means x should be equal to pi over 6, or 5 pi over 6. And those are our 4 solutions. Sine squared x equal 2 sine squared of x over 2. So this 2 sine squared of x over 2, our half angle identity is really nice, because our half angle identity is actually under a square root. So whenever we have square under it, we can cancel it. Therefore, this is actually just 2, and then our half angle identity without the square root, 1 minus cosine, right? 1 minus cosine, because it's not the cosine, x over 2. And then this crosses out, so then we'll have sine squared x equal 1 minus cosine x. Convert this into 1 minus cosine squared x. Right, it's not a proof, so we can actually manipulate both sides. This will get me, if I just erase the 1, right, and then this will get me cosine squared x minus cosine x equals 0. Which means cosine x or 1 minus cosine x equals 0. Or cosine x minus 1, I mean. So cosine x can be 0 or 1. So cosine x can be 0 or 1, which means x is 0, pi over 2, or 3 pi over 2. That's correct. Sine of 2x minus cosine of 3x equals 0. I actually if I think about it right now, it's probably best to group stuff in terms of stuff now. So we'll make this minus, we'll make this positive, we'll remove the parentheses, and then we'll add the sine x right here, and then we'll have the 2 cosine x plus sine 2x, and include that with the minus cosine 2x cosine x. What I'm trying to say is it's probably not a good idea to separate the cosine 2x. So this is if we I can't speak. I'm sorry. If we open this up, we'll have sine x cosine x, and then this is 2 sine x cosine x, so it'll be just 2 plus 2 sine x, right? And then minus cosine 2x cosine x. Now we have our cosine x, we can actually bring that all the way out. We'll have cosine x times 2 sine x, or cosine x times, 2 sine x, 1 plus sine x, minus cosine 2x. And now it's a lot clearer. It's actually a lot clearer now. I might have made a mistake. Please don't think that I didn't make a mistake. I might have actually made a mistake in this thing. But cosine 2x is equal to cosine squared x minus sine squared x. So that's just 1 minus 2 sine squared x. Right? Please don't ever think that I never make mistakes, because I do. And if I make a mistake here, please tell me that. This is 2 sine x, and this is plus 2 sine squared x. Right, this is minus. So minus and a minus means a plus, right? So we have 4 sine squared x plus 2 sine x minus 1 equals 0. And then we have this cosine x on the outside. And there you go. That's it. We're done. So our 2 solutions, all of our 6 solutions, which I won't get all of them. I won't tell you all of. There's no way I am going to solve for all of these solutions. Use a quadratic formula for this, because it's possible. Use a quadratic formula for that. But I can tell you 2 of the solutions are pi over 2 and 3 pi over 2. For the others, use a quadratic formula. I'm not going to tell you, because I am not going to solve for that. No way. And this review will probably take over an hour again. So it's fine. I'll cut some stuff down, definitely. Okay, more informational screens. So right here is everything about the law of sines. If you need any clarification, please put down in the comments. But basically, all of these are solvable with 1 solution. This is solvable with 0, 1, or 2 solutions. This is solvable with 1 solution if under this condition. Or this is solvable. Yeah, this has to be the condition. If it's smaller, it won't be solvable. This is unsolvable under any condition. You use law of sines for these. You use law of cosines for these. These are the law of sines and law of cosines. And this is the SSA rule for law of sines. Make the triangle, right? You have to make this triangle. I recommend you have the other one, the one that doesn't have the angle, the capital, and the lowercase, on here, right? I recommend you have it here, not at the bottom, because if you do it at the bottom, it's a lot harder to visualize what's going on with the 0, 1, or 2 solutions. So determine if A is big enough. So determine if this is big enough, because if it's not big enough, it'll just dangle. Right? If it's not big enough, it'll just dangle on. I drew it so that it looks like it isn't big enough, but it's actually way bigger than is needed, right? It's actually 0.7 bigger. So right there. So since it's big enough, there's 2 solutions. Draw the 2 solutions, right? Solve them. Solve the first triangle. And the second solution is, you see this B angle right here? You'll have B angle right here as well. So it's 180 minus B. That's the angle of the new B, right? Because you have this triangle, this thing, it's kind of swirls around this side right here. It swirls around like through a path of a circle, and then you'll get or like it rotates on a path of a circle, and then you'll have the new b right here where it touches a again, and then this is your new angle, which is 180 minus b old because of geometry, right? And then this will get you the new c, and then this is how you solve it. So we'll solve some triangles. Here are some extra formulas that you don't really need to know. Like this you definitely don't need to know. These two you probably do. But let's solve the triangle. 3, 4, and 6.2. So we don't have any sides, and it's SSS, so we need to use log cosine. Let's do C because it's easy, right? So C squared 6.2 squared. I'm gonna do this in my head. 3844. 6.2 squared equals 2 times 3 times 4, 24. Or minus 24 actually. So C squared equal A squared plus B squared minus 2AB cosine C. 9 plus 16 subtract over 13.44. And then that's minus 24. And then that's equal to cosine C. So C is going to be equal to, and I need to use my phone for this because I don't want to use the, I definitely don't want to use the computer for simple trivial matters like this. Put it in degree mode. 13.44 or the inverse tan. Where is it? Second inverse 13.44 divided by 24, and then make that negative, and then take the inverse. Okay, interest. Okay, so we have minus 34. That's our angle in cosine. Minus 34. Actually, no, that's sine. I use sine. I'm an idiot. 13.44 divided by 20. 13.44 divided by 24 is 0.56, and then take the inverse cosine. 56 degrees. Thank you. 56 degrees. And that doesn't make sense actually because it's a negative number and I didn't put negatives in there. 55.9. So we have 124.1 degrees. Now we can solve for the others using the law of sine. So 6.2 over sine. No, actually I'll put the sine on the top. So sine of the 124.1 over 6.2 is equal to sine of b, let's say, over 4. So our b is just going to be equal to the inverse sine or arc sine of 4 sine of 124.1 over 6.2. Let's continue. I'm just going to keep using the phone for a long time. Inverse sine. Okay, let's take 4 times this. No, fudge. Take 4 times 124.1, and the sine of that is equal to 3.3 divided by 6.2, 0.5, and take the inverse sine. 32.3 degrees. And then A is just 180 divided by 180 subtract all of these. That will get you that's about 156.4, so a 23.6 degrees. And that's your first triangle solved. Second triangle, we have 2 sides and 1 angle. I'm going to make this really small. That's 1. So our 2 is, we'll set it up like how I set it up. So we have 7 right here, and then we have 5 right here, and then we have 62 right here. So first step is I'll see if the 62 degree angle is enough for 5 to have no solutions, or 1 solution, or 2 solutions. So we'll do the h sine, or the to find the height, right? We'll find the height, and that's no 7 sine 62. See if it's bigger, equal to, or less than 5. So our 7 sine 62, or yeah, 7 sine 62, 62 sine times 7, that is 6.18, right? 62 sine times 7, 6.18, so this is not possible. No triangle. It's equal to 6.18, so there's no triangle. If you try to make a triangle, you would see that it will be equal to 5 over sine 62. You will see that it will be 5 over, or sine 62 over 5 equals sine b over 7, which if you input in the calculator, b will give you an error, and that and let me actually see if I will actually get an error from it. Times 7, divide by 5, and then this actually doesn't even fit into the domain. So take the sine inverse, that error. Yes, I'm correct. I'm not wrong for once. Thank you. Okay, so number 3. We have our number 3 now. This will be equal to A, B, and C. So our A's and our B's can really be anywhere you want. This will be 35. This will be 64. And this will be our 9.1. Right? We can use the law of sines for this. 35, 64. So this is 81. And then we can just do 81 over, or 99.1 over 81 sine equal b over sine of 64 equal a over sine of 35. And you know what, I'll leave you guys to do this problem by yourself, because I don't want to make this review any longer than it already is. But you should get b is smaller than 9.1 and a is smaller than b, right? That's how you check out if you're correct. You check if you're correct, because the closer the angle is to 90, the bigger your angle is. What did I say? The closer the angle is to 90, the bigger your side is supposed to be, right? The bigger your angle is, the bigger your side is, right? This 4, let's do 4, 8, 20, and 10. Now, if you look at this, you should know that it's not possible. You should note that it's not possible, because 8 plus 10 is smaller than 20, and you can't have that in a triangle, because you'll get something like this: 20, and then 10, and then 8, and that's just not possible. So that's number 4 right there. So no. We'll do some problems from the book now. So question 62 on the review makes us find. We don't actually have to solve for this triangle. It's just question 62 on the review. So I think this will last about 70 minutes, the review. Question 62 is, we want to find hiker and point A. So hiker is point C, so we want to find AC first. We have 70, 65. So this is not 65, this is 45. Right, so we want to find AC, so that's sine 45 over 80 is equal to, and you could see me switching the sines and the cosines sometime. It's just, I don't know why. And then this AC. And then AC is just going to be our nice little 8 sine 65 over sine 45. Right, and that is it. So B, what's the distance between the two canyon rims, which is the height? What's the height of the thing? That's a pretty fun problem. So we have this time 80. I'm actually going to solve this now, because I actually have to. So 80 sine 65 45 is, let's do 80 times 65 sine divided by 45 sine is 102. Wait, that's kind of illegal. 102 right here. Am I sure it's not? No, this picture is just really bad. 102.5. So this is 102, and that's 70. So to find the height, it's just 102.5 sine 70, right? From the other formula that we have whenever we try to find out the area, no, whether it has 0, 1, 2, or 2 solutions. Now we have this, and multiply that by 70 sine, gets you 96. The height is equal to 96.35. Right. So 38 on 5.6. Right. These are application questions. So and they're mostly going to use them log cosines and the log sines. A lot of them. I like application questions with these especially. So we want to find AB from this 860 by 175 feet with the 78-degree angle. So it's something like this: 860, 175, and 78-degree angle. And we want to find this. So what's this? So this is just 860 squared, c squared equal 860 squared, 175 squared. Let me input those onto the calculator. 850 squared plus 175 squared, which is 770,625. 225, I mean. And then we can actually do 2 times 860 times 175, which is 301,000. So plus minus 301,000. I'm just putting the k in there, and then cosine 78. So in order to get this, we just do the 301,000 times the 78 cosine, which will get you, that's actually not that much, 62,581. And then take that, subtract from 770,225, which will get you minus 707, no, not minus, 707,643. And then take that and take the square root. Right, so 707,643, take the square root. That which will give you roughly 841. 0.21. 841.21. There you go. So 43 on 5.6. Trigonometry and geometry. We have our cube right here. I can actually draw these quite well, like that. We have this as 1, 2, and 3, and what we want to find is the angle of this. What's this angle right here? So in order to find this angle, well, we actually have to draw a triangle like this, right? And we have to find the sides, each side. So what's this side? We have 2, 3, so that's square root of 13 by Pythagoras. 1, 3, square root of 10 by Pythagoras as well, and 2, 1, square root of 5 by Pythagoras. So this is literally our arsenal right here. So we have c squared, 5 squared, or 5 equal a squared plus b squared plus 2 times a, no, not plus, I mean minus 2 times ab cosine of c. Cosine c. Right, so this is going to end up being c is equal to the inverse cosine of 10 plus 30 minus 18 And then since we have minus 18 and then this 2, so it'll just be minus cancels out. 2 over 2 square root of 130, and I will input that into my phone right now. We have 9 divided by 130, take the square root of it, which gives you that, and then take the inverse cosine. 37 degrees. 37.9. 37.9 degrees. Final question. Our final question is question 40 from 5.6, which is navigation. Two airplanes flying together in formation take off in different directions. One flies east at 350. East at 350. If you remember your directions, one flies east at 350. And then the other flies east northeast. So let's pretend this is our island right here. East northeast. East northeast is basically northeast east, but it's east northeast, so it's 67.5 degrees from north. So it'll be something like this. So and then how far apart are the two airplanes 2 hours after they separate, assuming they fly from the same altitude? So we'll have 350 east, so that's 700. And then east northeast, so that's 760. And the two airplanes are, well, it's probably something like this. So we want to find the shortest distance between the two airplanes. The angle is 22.5 degrees because this is east northeast, and then this is just east, right? So north northeast, northeast, east northeast, east. Yeah, this is what that's what's going to get you, east northeast and east, 22.5 degrees. We want to find this. We just plug it into the formula, right? The formula is the law of cosines, 700 squared, 490k. So this is c squared equal 490,000 plus 760 squared, which I'm actually going to use the calculator for that. I could do it in my head, but I'm not going to. 577,600. And then that's 2 times 760 times 700, so 1.064 million, right? And it's not supposed to be a plus there, it's supposed to be a minus. Cosine of the 22.5. So what this will get you is 490,000 plus 577. I'm gonna do all of this. 490,000 plus 577,600. Right, and then minus this by 107,600 minus no. Take the 1064000 and then multiply that by the cosine of the 22.5 cosine. That's what you'll get, and then subtract that from 1067600, and then take the negative O off, and then take the square root. So they are about 290 apart, 290.8 feet, 290.8 miles apart. That's going to be it for today's review. If you liked it, press the like button, or just save my suffering of recording 1 hour and 20 minutes of a review. Even though it's only 13 pages, I tried to pick the best problems. Few laws of cosines, few laws of sines, but mostly just a bunch of fun. And that's going to be it. If you want me to do more problems, I don't know why you would. I know that there will be a final in a few months, and that is going to be a bunch of big deal. So I'll probably do a stream to do that. No big outgoing, no big what am I saying? No big announcements, no big definite announcements yet. Still all a work in progress, but I hope I will get to you right then and there, or really soon, as I make the chapter 6, chapter 7, chapter 8 reviews. So that's going to be it. I'll see you later, and good luck on the test, I guess.